So, collision theory is the theory that's used to help explain why reactions happen in the first place and why different factors affect the rate of chemical reactions. So, you should be able to recall and evaluate the statements about collision theory. So, in order for particles to react together, they must one, collide in the first place, two, they must collide with the proper orientation or geometry, and three, they must collide with sufficient kinetic energy or speed to overcome what's called the activation energy. So those are really the three conditions. Sometimes they might say in order for colliding particles to react, they must. And then if they include the collision part in the initial statement, then there's really only two things that need to happen. They need to collide with the right orientation and with enough energy. Okay, so proper orientation, that implies that when particles collide, sometimes one atom or one part of one reactant needs to hit a particular atom on another molecule, another reactant molecule. So in this picture, you have a couple of collisions where the one atom on this reactant is not hitting the right part of the next reactant, and so those are what are called ineffective collisions, and so no reaction happens. But an effective collision would involve this atom here, this nitrogen atom, colliding with this part of the ozone molecule. And so there we have the effective collision happening, which leads to a successful reaction. So the idea is that all of these things are occurring at all times within a reaction mixture. You've got reactants colliding into each other, but theoretically, only the ones that collide properly with the right atoms colliding in the right way lead to successful reactions. And there's not really any way we can influence how often, what proportion of the collisions are effective or have the proper orientation at least. But what we can do is we can try to make just more collisions happen more frequently. And by doing so, we'll get more successful, effective collisions. But the proper orientation thing, besides knowing that it's part of collision theory, is not something that we're going to reference back to very often in this topic. The other key idea here is activation energy, that when particles react, there is a minimum amount of energy required that they must have when they collide in order to bring about a chemical reaction between the particles. And generally, that energy is thought to be associated with the chemical bonds that already exist. So in this reaction above, nitrogen is bonded to oxygen, and oxygens are bonded to oxygen within the ozone molecule. And in order for new products to form, the bonds within the reactant have to be broken. And so that's what's called the activation energy, the minimum energy required to bring about a successful reaction. And so for reactants to turn into products, you go from the initial energy or enthalpy, the stored energy of the reactants, and to the top of this hill on an enthalpy level diagram, that's what represents activation energy. We can label it as E sub A is the symbol for activation energy. So it's the minimum energy required for the reaction to happen. In the reverse reaction, when we get to the equilibrium topic and we talk about reactions going forwards, but also backwards, the activation energy is from where the products are, their initial energy, to the top of that same activation energy hill. So this blue one represents the activation energy of the reverse reaction, and the red one represents the activation energy of the forward reaction. And so that is the minimum sort of energy requirement, the energy hurdle that particles need to have when they collide in order for a reaction to happen. So there are a bunch of factors that we can influence when we're carrying out a chemical reaction. And based on what we do to those factors, we can increase or decrease reaction rates. And we should be able to explain why we would expect them to increase or decrease the reaction rate. So surface area is one of those factors. Surface area only affects solid reactants. And by crushing solids up into smaller pieces, and especially into powder, we greatly increase the amount of surface area that is exposed. And by exposing more particles, exposing more surface, we end up increasing the frequency of collisions, or the number of collisions per unit time. One thing that you cannot say is you can't just say that increasing the surface area increases the number of collisions, because the total number of collisions may end up actually being equal. What really matters is that more collisions are happening more often. So make sure you say frequency of collisions or more collisions per unit time. That's really important. And we're going to come back to this reasoning again and again and again for a number of the different things that we can change. Surface area, just be aware of the common misconception. By making smaller pieces, we actually make more surface area. So don't let that bit confuse you. Concentration, usually reserved for talking about aqueous solutions, talking about the molarity of a solution, but we can also talk about this for gases. And again, when we change the concentration, we are affecting the frequency of collisions. So by using a 2 molar solution instead of a 1 molar solution, there's more particles in the same amount of space. So they're just naturally going to bump into each other more often, which is why solutions that have higher concentration end up reacting more quickly than solutions that have low concentrations. Temperature, the one probably everyone is most aware of, temperature absolutely affects reaction rates. High temperatures lead to faster reactions, and low temperatures lead to slow reactions. And most people have sort of a gut sense about that. There's actually 2 reasons why temperature is believed to have that impact. One, that same frequency of collisions argument. Temperature has to do with the kinetic energy of particles. And so when we increase temperature, we increase the kinetic energy or the speed of reactant particles. And so if particles have more speed, they will collide with each other more often, number one. But actually, more importantly, this reason, when they collide with more speed, more of those collisions will have sufficient energy to overcome the activation energy. So with temperature, you can give 2 explanations for why reaction rate is affected, but the more important reason has to do with that minimum energy requirement. It's really important when talking about temperature to talk about kinetic, to use the word kinetic in your description of energy, because temperature is a measure of kinetic energy of particles. So lowering temperature of something lowers the average kinetic energy or speeds of the particles, and therefore less of them, when they collide, have enough energy to react. They also collide less often. The final reason or way that we can influence a reaction rate is by adding a catalyst. Catalysts are not relevant for all reactions, but for many there are specific catalysts. You aren't really expected to know specific ones at this point in time. When we do organic chemistry, there may be a couple that you need to be aware of. The way a catalyst affects the reaction rate is a catalyst actually provides some sort of alternate way for the reaction to happen. It's sometimes called an alternate pathway that has a lower activation energy. So the key takeaway is that a catalyst lowers the activation energy. It lowers that minimum energy requirement. And as a result, more of the reactant collisions, reactant particles, are going to have enough energy to successfully react. And so the way that we would annotate that on this enthalpy diagram is that that hill would become lower. And so now, instead of the activation energy being all the way up from reactants to the top of that blue hill, it's just from where the reactants are to the top of this hill. So it's a much lower hurdle. It's also lower for the reverse reaction. So both activation energies get lowered by the same amount, and it would make both forward and reverse rates faster by the same amount. So adding catalysts lowers the activation energy requirement. It provides this alternate way for the reaction to happen, and that means more particles have enough energy to successfully react. That makes the reaction happen much more quickly. And catalysts can speed up reactions millions and billions of times. And one of the best things about catalysts is that while they are involved in the reaction, they don't get consumed by the reaction, so they don't get used up. They might react in one step, but then later they would be regenerated and reformed so that overall their concentration doesn't change. They might also just provide a surface upon which the reaction can take place. And so catalysts themselves can actually be modified by these same 3 factors up above to doubly affect the reaction rate. So what I mean by that is that if you took a catalyst and you crushed it up into more pieces and gave it more surface area, that would make it affect the reaction rate even more because of reason number 1. You would have provided more surfaces upon which the catalyst could affect the reaction. And if you make the catalyst hotter and warmer, number 3, well, then you're going to increase how much the catalyst can affect the reaction rate. So catalysts themselves can be modified in a way that affects the reaction rate. The final thing to come around to has to do with the shape of this curve, and now we can explain it based on collision theory. So why do the curves that we're going to look at always start off steep, then get slower and slower, and eventually plateau? Well, it comes back to collision theory. At the beginning of any reaction, we have the highest concentration of our reactants. And so highest concentration means the most frequent collisions, and means the fastest reaction rate right off the bat of a reaction. And that's why we get the steepest graphs. The steepest graphs means they have the highest slope. Highest slope means fastest rate of reaction. Over time, as reactants get consumed, get used up, and usually that would lead to a less concentration, or for a solid, less surface area. As those changes happen, the reaction naturally starts to happen slower and slower because the collision frequency is less and less. And we see that with the graph getting less and less steep, and eventually it flattens out when there is no more reactions taking place because one of the reactants has been consumed. So again, it's steepest at first because it's fastest at first, with highest concentrations and highest frequencies of collisions. And then as concentration or surface area decreases over time, the frequency of collisions goes down and the reaction rate goes down. So that's a look at collision theory and the different factors that affect reaction rate. And these bold things on the right that I've circled, these are the key IB reasonings that you're going to be able to use and get credit for on the IB exam.